So, main reason in order to get the constant or fixed VPOS 4.6 volt is that we cannot afford any noise here, and since we are refreshing this OLED pixel at a particular frequency, a refresh rate. So, when it is not getting sampled, the basically the current, and the current is determined by the VGS of this MOSFET MP1. So, when we are not sampling, any changes in this VPOS will basically cause a change in the current. If it is a high frequency, it is quite possible that this capacitor will act as a short, and it may try to suppress some of the noise, but any low frequency may not get suppressed. So, we may get a flicker, and if it is order of, let us say 100 hertz or below, we can easily get flicker which will be visible to our eyes. So, that is why we need a very clean 4.6 volt, and VNAG is programmable from minus 1.4 volt to minus 5.4. As I mentioned, some of the newer devices require as low as minus 0.88 volt. So, let us see why we require a variable negative voltage. So, when we are changing the brightness, what we are doing basically, we are changing the current. We know LED requires constant current, as we saw in the backlight LED driver. So, your brightness can be controlled by simply changing the current. So, once we change the current, so let us say we are reducing the current, which means we are reducing the brightness. So, what would happen actually when we reduce the brightness, and we know the forward voltage is depending on your current. Higher the current, more the forward voltage this OLED will have. So, when I reduce the current, this LED or organic LED will require lesser forward voltage. If I do not change, let us say I keep it fixed to minus 5.4, okay, and this is fixed to 4.6 volt. So, what is the total voltage from positive to negative terminal? It is 10 volt, okay. And now let us say, and we know this current, this is a current source. So, it will require some headroom in order to keep in saturation, and that may not be very large, maybe like let us say 400, 500 depending upon these are high voltage devices. So, obviously, it cannot be 100 millivolt, it will be slightly larger. So, let us say 500 millivolt roughly, okay. So, 500 millivolt minimum you require VDS here. So, out of this 4.6 volt, 500 will be dropped here, okay. So, this LED will see 4.1 volt, and in order to, let us say, even in order to simplify more, we can even say like 600 millivolt. So, you will get a 4 volt here. So, 4 minus 5.4. So, let us say this is not 5.4 or minus 5 volt, okay. So, you are getting a 9 volt across this, correct. When I reduce the current, let us say the forward voltage is reduced to 5 volt. So, what does it mean? You need to reduce by 4 volt this. So, when it is a 5 volt, you have a 4 volt here, correct. So, you require a minus 1 volt only at the other end, not minus 5 volt. I mean, you can, your current will still be constant, okay. So, what would happen if you keep this at fixed at minus 5 volt? What would happen? This LED forward voltage will not change. I mean, depending upon the current, it will adjust itself, okay, because we are, it is having a constant current. So, whatever the extra voltage we have, it will be dropped, absorbed by this, okay. So, this node, drain node will automatically. So, if it is it's a minus 5, if it is minus 5 volt, and let us say the required, so 4 volt and minus 1 volt, 5 volt was the required. Now, if I keep fixed at minus 5 volt, so 4 minus 5 is 9 volt, okay. So, but the problem here is this, since this current is constant, so this voltage has to drop, correct. So, the because we are having a constant current, so we know that this voltage has to go low when you are reducing the current, because this LED has to maintain its forward voltage. So, what would happen? The VDS across this MOSFET will increase, and which means the dropout voltage is increased. So, if the dropout voltage is more, then what would happen? It will have higher losses. So, it will impact your efficiency actually, that is the main reason, okay. So, do not misunderstand that this voltage is controlling the brightness is still controlled by the current, okay. So, this voltage has nothing to do as such with the controlling the brightness, but mainly due to the efficiency reason we want to control this voltage when we are controlling the current in order to change the brightness, okay, so that we can maintain the dropout voltage across this MOSFET. Okay. So, just like in LCD, there are like certain power up and power down sequencing requirement here as well. So, AVDD is enabled first and then we enable positive voltage, which is VPOS, and then VNEG. So, the VPOS and VNEG follow the similar sequence like we had in LCD. So, AVDD is analog voltage and it comes up first. So, it basically settles all the bias voltages and everything before we turn on these LEDs actually. Okay. So, by default when your AVDD, we know it is regulated at 7.7 volt, okay, and this is control voltage S wire. So, we have a separate just like in the backlight we had a separate enable signal for backlight, there is a separate enable signal for AVDD, but your positive and negative supply are controlled by a single enable signal which we called S wire or control signal, and the same signal is used to program the this negative supply also. So, it is a single wire control which enables as well as control the level of this negative supply. So, by default VPOS will go to 4.6, it will remain there, and by default this VNEG goes to minus 4 volt. Okay. So, if you do not do any programming, which means you just turn on, then by default it will go to minus 4 volt. Okay. So, how do we generate these three supplies? The concept remains same, just like in LCD. We require one boost converter in order to generate 7.7 volt. So, this right hand side AVDD, and another boost we require to generate 4.6 volt, because we know the battery voltage is 2.7 to 4.6 volt. So, most of the time it is below your output voltage. So, you need to boost. In this case it is always higher than your input. So, you need to boost here as well, and for negative supply we use inverting buck boost. So, we cannot use charge pump here. The reason is one is current requirement is higher like 300 milliamp or so. So, it is not easy to build a high current charge pump. Other issue is it is programmable actually. So, we need to program it, and with the charge pump we need a fixed voltage, it is a discrete actually, not continuous. So I mean you can use LDO, let us say charge pump and then LDO drop the voltage, but it will be highly inefficient. So, that is why we always use inverting buck boost here. So, let us see how we program this negative voltage using that S wire, the single wire control or the control signal CTRL. So, what happens, there are some timing requirements. So, T initial timing is actually 300 microsecond typical and 400. So, this is the time delay which is given before you even turn on this 4.6 volt or positive supply. So, and then after that you have this is basically the short circuit protection. So, the 10 millisecond wait is given before you turn on the negative supply in order to make sure that short circuit is not there. So, let us say somebody has shorted, okay. So, your supplies will not ramp up. So, basically it is a more like a timeout signal you can say. So, when the 10 millisecond is passed and still your supply is not ramping up, okay, then so I mean we know that we need to turn on positive supply first and negative later. We do not want any instance where negative is turned on and positive is not there. So, and let us say that there is a short circuit at the positive voltage, so it will not ramp up at all. Okay. So, if you are not monitoring VPOS and you just give a 10 let us say 1 millisecond delay and after that you turn on negative supply. Okay. So, what will happen? Positive supply will not come up and negative will go high, and there is a risk of damaging your panel here. So, that is why we give this much time. So, we wait for 10 millisecond and keep monitoring this positive supply. If it does not come up, we flag the short circuit. If it has already come up within 10 millisecond, then we turn on the negative supply. Then this is your T low, which is nothing but off time of this. So, the way it is programmed, you send pulses. So, at first positive edge will be basically the first positive edge will be acting as enable, and after that any positive edges will act as a programming signal. Okay. And there is some timing requirement. These pulses should not be wider than 25 microsecond and shorter than 2 microsecond. Okay, so
short circuits are checked between positive supply and ground and negative supply and ground.
anything actually, it's the negative, positive, zero, anything. I mean, supply short circuit can happen with any, like negative can be shorted to VDD or it can be shorted to ground. So, all checks are there actually, all kind of short circuit checks. So, similarly to the T high, so they have the same timing as T low. So, it is nothing but on and off time. And then T store. So, what happens once you send the pulses? So, let us say I send this 10 microsecond on and 10 microsecond off pulse. So, in order to get the first pulse, you have to first pull it down and then wait for the minimum pulse width required 2 to like 25 microsecond any. So, let us say I fixed it 10 microsecond. So, you keep it low for 10 microsecond and then keep it high. So, this will be treated as first stage of the programming. Okay. And then after that it will keep counting, and the reason we have a 25 microsecond because 30 microsecond is the store. Okay. So, after 30 microsecond if no pulses come, then it will be acting as store. So, within 30 microsecond if you get let us say one more pulse, then it will keep basically programming, and after 30 microsecond only it will latch the output. Okay. So, let us say you have a counter and you keep counting this. So, here we have 1, 2, 3, 3 rising edges. So, after 3 rising edges until so this last after last edge then you wait for 30 microsecond and you see if there are any edges. So, if no edges are coming, then you latch the output and then set the negative voltage, that is it. Then when you have a negative edge, then again you wait for this 30 microsecond, and 30 microsecond is basically then it is like a shutdown. Okay. So, if it remains low for more than 30 microsecond, then it will be treated as shutdown, that is it, because this is acting as both enable and disable. So, that is why. And this T off can be maximum off. I think T off is basically you turn off everything. So, it is just like the same. So, you shut down and then turn off everything. So, it is minimum 200 microsecond. So, by default VNAC turns on with minus 4 volt as I mentioned earlier when S wire goes high, and then it is programmed by sending those pulses where you count the positive edges of each pulse. So, VNAC is predefined at 1 pulse positive edge and then reduces by 100 millivolts. So, what it does basically, 1 pulse is internally programmed. So, by default we know it will go to minus 4 volt, and there is one more thing actually. So, we know the positive voltage and negative voltage, there is a roughly delay of let us say 10 millisecond. So, before positive edge comes, if you do not do any programming, then it will by default it will go to minus 4 volt. But let us say you send some pulses here in between before it comes up, then it will take the new value actually. So, even you can make it this I mean before it starts you can program it. Instead, if you do not want it to go to minus 4 volt, you can do that as well. So, then if you send one pulse, then one pulse is already prefixed. I mean in hardware you basically this programming is done. So, minus like one pulse is already programmed to minus 5.4 volt. So, when you send only one pulse and let us say you keep it high after that, which means you basically lapse this 30 microsecond time, and so what it will do, it will go to minus 5.4 volt. So, and then after that every pulse it comes, it will be reducing by 100 millivolt. Okay. So, this number of pulses will be always counted from single pulse reference. So, we know one pulse is minus 4 volt. So, if I send a 2 pulse let us say, then it will be reduced by 100 millivolt. So, you will get minus 5.3. So, that is how. So, one pulse, whatever the one pulse, I mean it may vary from part to part actually. Some, let's say you get one TI part and one, let's say, ST part, okay. So you have to look at data sheet, what is one pulse they have set in there. So it's not necessary that all devices will have minus 5.4 volt. One may have minus 4 volt, other may have minus 5.4 volt. So then after that, whatever number of pulses you send, and based on that you program. So let's say if I want this voltage to go to minus 5 volt, okay. So you have to send 5 pulses. So 5 minus 1 is 4 into 100 millivolt. So it will go to minus 5 volt, and that's how you program actually. So this is your this is taken from TI data sheet itself. So they have a single pulse voltage, you can see here. So no pulse minus 4 volt, one pulse minus 5.4. After that, as number of pulses increase, this voltage will keep reducing. So you can say the at 41 pulse it goes to minus 1.4 volt, because 41 is n minus 1, 44 volt. So minus 5.4 minus 4 is 1, yeah, plus sorry, minus 5.4 plus 4 volt is minus 1.4, and these are the DAC values actually. So these pulses will be basically counted and then will latched, and we know that these voltages can be programmed using DAC. So let's say if a feedback resistor, okay, so you can just program the feedback resistor and get different values. So those will control these voltages, that voltage DAC or resistive DAC, whatever, or you can change the reference also if you have. Okay, so this is again TI part, TPS 65632, which is used in most of the phones actually. So it has 3 supply, we can see here left hand side AVDD boost, so 7.7 volt, 30 milliamp. So this only supplies analog supply, so it does not require very high current. And then right hand side you can see we have this positive boost 4.6, 300 milliamp, and then this one is your negative buck boost, which is minus 4 volt, 300 milliamp. So minus 4 volt is the default, but it can be programmed using this control signal CTRL, which is nothing but S wire, this guy. Okay. Okay, so there is an issue with this positive AMOLED boost converter, and we know it requires fixed 4.6 volt. So and your battery voltage, so let us see here, battery voltage we know it is going from 2.7 to 4.6 volt. Okay. So what would happen when you are very close to your maximum voltage, battery is let us say fully charged, then you can hardly regulate the output 4.6 volt. Even if you make a let us say 100% 0% duty cycle, you just bypass this, okay, it is a boost. So 0% duty cycle means V in equal to V out. So there will be some IR drop, the current is drawing, so it will be always less than your input. So we can hardly regulate at 4.6 volt, it is very difficult. So that is the main problem. So that can be fixed by again boosting this voltage. We know that we can always boost it higher than. So if it is a 4.6 volt, we can easily achieve more than 4.6 volt. So let us say you make it 4.7 and 100 millivolt you drop in this LDO, just like we were doing for LCD, if you remember. Okay. So you can get 4.6 volt easily. Okay. There is one more technique I have not mentioned here in order to, so this will have obviously some loss in efficiency due to this dropout voltage, but you have to live with it because that is the only way to regulate the output. There is one more technique. So we know that if let us say this MOSFET is MP replaced with a diode, so it will become non-synchronous, correct, and non-synchronous the diode drop will be higher compared to IR drop of this MOSFET, because the on resistance of this is much smaller. So what we can do actually, when voltage V in is very high and we know that it is going out of regulation or your duty cycle is saturated to 0%, near 0%. What you do, you fully turn off this MOSFET and it will conduct through body diode. So, it will basically enter into non-synchronous mode and the drop will be more. So, basically you are dropping the voltage across that diode, the similar you will get a similar basically functionality what you are achieving with this LDO. Okay. So, without adding an this LDO, you can still regulate the output by entering into non-synchronous mode and conducting the current through body of this MOSFET.